Good morning, everyone. In this class, we're going to continue our discussion on growth of functions. In our last class, we introduced the notation of big O. Today, we're going to introduce the concept of big omega and big theta. If we recall the definition of big O notation, then let f and g be two given functions, either from a set of integers to a set of real number, or from a set of real numbers to a set of real number. Then we say f of x is big O of g of x if there exists two positive constants c and k, such that we can satisfy this inequality that absolute value of f of x is less than equal to c times of absolute value of g of x whenever the x is greater than k. If f is big O of g of x, then we can also say g is asymptotically dominates your given function f. And these two positive constants c and k, they called as the witness with respect to this relationship that f of x is big O of g of x. Graphically, we also learn that big O gives an upper bound on the growth of a function. So let's suppose we have two given function f of x and g of x, which is represented here by this black and green curve. Then for a positive constant k and c, we can see here that c times g of x is going to dominate your given function f of x after the value of x becomes larger than k. Okay, so for every x greater than k, we satisfy this inequality that the absolute value of f of x is going to be less than equal to c times of the absolute value of g of x. So this has a meaning that f of x is big O of g of x by using definition of big O. Okay, so here we get an upper bound on the given function f of x, and we can say f of x is less than equal to c times of g of x. So this term c times of g of x is going to dominate my given function f of x in this region whenever your x is greater than k. We can look at one example. So that we have this given list of functions where the first function is n log n with the base 2, n square, n factorial 1 2 to the power n log n with base 2. Can you put them in increasing order based on their growth? And by using this big O notation definition, then these functions can be put in increasing order based on their growth. The first function will be the constant, is going to be big O of 1. Then we have a logarithmic, which is big O of log of n. Then it's going to be the linear function big O of n. Then it's going to be a linear arithmetic function, which is big O of n log of n. Then it's going to be a quadratic function big O of n square. It's going to be exponential function big O of 2 to the power n, and it's going to be factorial. It's going to be at the last big O of n factorial. There are going to be infinitely many functions exist in between this order. For example, here you can say after order of n square, you could have big O of n square log base 2 of n. Then you could have big O of n cube. You could have big O of n to the power 4, and there are many functions exist in between any two given functions here. The general rule of thumbs based on the growth of the function. So any function up to here, starting from a constant to linear arithmetic, they are considered to be a good function in computer science because of their growth. Their growth is very slow. And any function after this big O of n log n, they're considered to be a bad class of function in computer science because of their growth. Okay. The interesting thing which you can notice that if you compare n and if you compare n times log base 2 of n, and if you start putting some really big number, let's suppose n 100 and 10 to the power 4 n equal to 10 to the power 9, then you will see that for a really large number, let's suppose n 10 to the power 9, then this function n log of n base 2 is going to be approximately equal to 30 of n. Okay, and because of this result, you can say this n log of n function, they have a very similar growth as your linear function. So you can say n log base 2 of n has similar growth as n. Okay, you can try this experiment. You can try to plot these two functions just by taking some really large value of n and see how the behavior of these two functions. You will see that for a really large value of n, n log base 2 of n is going to be approximately 30 of n. Let's take another example about this big rotation. But before taking this example, I just would like to mention that big O is sometimes also called as a big OOH. Let's suppose we have an example and we want to compare log n with base 2 with your n. Then can you compare based on your big O estimate? So we have two functions. One is a log of n with the base 2 and one is your n. And we want to relate them. Now to compare these two functions, log of n and with n, we can use one of the inequality which we proved in our mathematical induction. Then we know that for n greater than 1, n is going to be less than 2 to the power n. Okay, and taking log both sides, so we get this side will be your log of n and this side will be your log of 2 to the power n, which is going to be equal to log of n less than n times log of 2, which is going to be equal to log of n divided by log of 2 is less than n, which implies that log base 2 of n is less than n. Okay, this is going to be true for every n greater than 1. So from here we can choose two constants, c equal to 1 and k equal to 1. Then by definition of big O, we get that log base 2 of n is big O of n. Okay, so that's going to be our final solution. So if you want to compare log of n with base 2 with n, so you can make a statement that log n with base 2 is big O of n. This time let's suppose we have another kind of problem. Can you find the big O estimate of this given function f of n, where f of n is 3n log of n factorial plus n plus 3 times of log of n. Now to get your big O estimate of this function f of n, let's rewrite this given function f of n as is going to be 3n times log of n factorial plus n times of log of n plus 3 times of log of n. Okay. Now can you find a function g of n, and can you find these two constants c and k such that you can show that f of n is less than or equal to c times of g of n for the value of n greater than k. Okay, so this we want to prove it. So we can use a result which we did in our last lecture for n greater than 1. N factorial is 1 times, 2 times, 3 times, 4 times, all the way up to n minus 1 times of n, which is less than or equal to n times, n times, n times, all the way up to n minus 1 times of n, less than or equal to n to the power n. And by taking log of both sides, we get log of n factorial is less than or equal to n times log of n for all value of n greater than 1. Okay. So from here we can say that log of n factorial is big O of n log of n. Now using this second result in your equation 1, we can write our f of n is going to be less than or equal to 3 of n times n log of n plus n log of n and plus 3 log of n using second in first. Okay, which is less than or equal to 3 of n square log of n plus n log of n plus 3 log of n, and which you can say is less than or equal to 3 of n square log of n plus n square log of n plus 3 n square log n, because for n greater than 1 we have n square log of n is going to be greater than or equal to n log of n, and log of n is going to be less than or equal to n square log of n. So we'll use this inequality here as well as here. Okay, so this side is going to be less than or equal to, you have 3n square log n plus n square log n plus 3n square log n, so it's going to be 7 n square log of n. Okay, so we proved that f of n is less than or equal to 7 times of n square log of n for n greater than 1. Then by taking c is equal to 7 and k is equal to 1 as a positive constant, definition of a big O gives us that f of n is big O of n square log of n. Okay, so that's going to be our final answer. So this way we can prove that this given function f of n is a big O of n square log of n. After this big O notation, which gives us the upper bound on a given function, we're going to discuss the big omega notation, which we generally denote by big omega, where omega is an uppercase version of your lowercase Greek letter omega. So the definition says that f and g be two functions either from a set of integers to a set of real number, or from a set of real number to a set of real number. Then we say that f of x is big omega of g of x if there exist two positive constants c and k, such that we can satisfy this inequality that absolute value of f of x is greater than or equal to c times of absolute value of g of x whenever your x is greater than k. So we will write that f of x is big omega of g of x, or we can also say that f of x belongs to big omega of g of x. Okay, because big omega of g of x is the set which contain all those functions which satisfy this inequality. So if you remember, in case of big O, that gives an upper bound on the growth of a function, while the big omega gives a lower bound on the growth of the function, which we can understand through this figure. So let's suppose you have a given function f of x and g of x, which is represented by this red color and green color curve. Then if we can find two witness c and k such that the behavior of this function g of x changes, that c times g of x will be this black color curve. And if you notice the behavior of these two functions f of x and c times g of x, then in the region when x is less than k, so this curve c times g of x was dominating your given function f of x, but when you cross this region of x is equal to k and you go x greater than k, so in the region of x greater than k, the behavior of this function will change, and now f of x will dominate your c times g of x. So c times g of x will give a lower bound on the growth of the function. Okay, so it will give a bound from the below. One of the important relation between big O and big omega can be seen here in the form of this statement. So you are saying f of x is big omega of g of x if and only if you can prove that g of x is big O of f of x. And by definition, you can write the proof of this statement. Okay, let's take one example and just to realize how these two things are connected. How you can say f of x is big omega of g of x if and only if g of x is big O of f of x. So in this example, we have chosen f of x as 8x cube plus 5 of x square plus 7, and my g of x function is x cube. Now let's suppose on the left hand side I have chosen to show that f of x is big omega of g of x, while on the right hand side I will show how this g of x is big O of f of x. Now my f of x is going to be equal to 8 of x cube plus 5 of x square plus 7, which I can easily say is going to be greater than or equal to 8 times of x cube for every x greater than 1. Okay, so by taking the constant c is equal to 8 and k equal to 1, the definition of a big omega gives that f of x is big omega of g of x. While to show that g of x is big O of f of x, we have f of x is equal to 8x cube plus 5 of x square plus of 7, which we can easily show is going to be less than equal to 8 plus 5 plus 7 is going to be your 20x cube for every value of x greater than 1. Then by taking c equal to 20 and k equal to 1, definition of a big O gives that f of x is big O of Now to show that g of x is big O of f of x, we have to show there exist two positive constants c and k such that my g of x is less than equal to c times of f of x for every value of x greater than k. Okay. For f of x equal to 8x cube plus 5 of x square plus 7, we can show is greater than equal to 8 of x cube for every value of x greater than 1, and this implies that 8 of x cube is less than equal to 8 of x cube plus 5 of x square plus 7, which on dividing by 8 both sides will obtain that x cube is less than equal to 1 divided by 8 times of x cube plus 5 of x square plus 7, and then this is my g of x is less than equal to 1 by 8 times of my f of x for every value of x greater than 1. Okay. Then by taking c equal to 1 by 8 and k equal to 1, we get g of x is big O of f of x. Okay, so you can see here that why these two statements they are equivalent. The next notation which we are going to study in this course is a Big-Theta notation, which we denote by as big and theta, and theta is an uppercase version of your lowercase Greek letter theta. So by definition, let f and g be two functions either from a set of integers to a set of real number or from a set of real numbers to a set of real number. Then we say that f of x is Big-Theta of g of x, or we can also say as f of x is of the same order as g of x, or these two functions will be of same order if there exist positive constants c1, c2 and k such that we can satisfy this inequality that whenever x is greater than k, then the absolute value of f of x is less than equal to c2 times of absolute value of g of x, and absolute value of f of x is greater than equal to c1 times of g of x. Okay. So equivalently, we are saying that f of x is Big-Theta of g of x if and only if f of x is big O of g of x and f of x is big omega of g of x, because If f of x is big omega of g of x, we can satisfy this inequality provided we have two positive constants k and c of 2. And if f of x is big omega of g of x, then we can satisfy this inequality provided we have a constant, and the constant here it should be c of 1. Okay, such that my absolute value of f of x is greater than or equal to c1 times of absolute value of g of x. And from the definition of big O and big omega, we can say if f of x is big O of g of x, and if f of x is big omega of g of x, then f of x is big theta of g of x. So this big theta notation will give us the lower as well as the upper bound on a given function. So in our first problem, we have to show that if f of x is 3x squared plus 8x log of x, then show that f of x is big theta of x squared. Now from this definition, we can show that f of x is big theta of x squared if we can prove that f of x is big O of g of x, and if f of x is big omega of g of x. Okay, so let me write the solution here. So let g of x is my x squared, and then you can prove f of x is big theta of g of x if and only if f of x is big O of g of x, and if you can also show that f of x is big omega of g of x. Okay, so I'm using this equivalent definition. My first point, I'm going to show that f of x is big O of g of x. Okay, so my f of x is defined as 3x squared plus 8x log of x, which I can easily write is going to be less than or equal to 11 of x squared, and this is true for any x greater than 1, since my x log of x is less than equal to x squared. Okay, so if you use this inequality here, you can show that this f of x is less than equal to 11 times of x squared. Then by taking c constant as 11, okay, and this k as 1, by definition of big O, we get the 3 of x squared plus 8 of x log of x is big O of x squared. And you're done with the proof of this first statement. Now to prove this second statement, that f of x is big omega of g of x, we take our f of x, which is going to be equal to 3 of x squared plus 8 of x log of x, and this we can say is going to be always greater than or equal to 3 of x squared for x greater than 1. So then by taking c constant equal to 3 and k constant equal to 1, your definition of big omega gives us that f of x is big omega of g of x. And we are done with the proof of this statement. Then finally we write on combining f of x is big of g of x and f of x is big omega of g of x, we get f of x is big theta of g of x. And that's the proof of this example. Our second example is we have to show that the sum of the first n positive integers is big theta of n square. There could be many different ways you can show that the sum of the first n positive integer is big theta of n square. We're going to take the simplest way. So we know by definition of big theta, if we can prove that f of n is big O of g of n and f of n is big omega of g of n, then combining both the proofs we get that f of n is big theta of g of n. Okay, so let me first define my f of n function, which is the sum of the first n positive integer. So that's going to be equal to 1 plus 2 plus 3 all the way up to n. Okay, and I also choose my g of n, which is equal to n square. So first I'm going to write a proof that my f of n is big O of g of n. So we take our f of n, which is the sum of the first n positive integer, as 1 plus 2 plus 3 all the way up to n. And we have learned in our summations that the sum of the first n positive integers is nothing but n times n plus 1 divided by 2. Okay, so you can say using sums. So my given function f of n is now equal to n times n plus 1 divided by 2, because I know the formula for the sum of the first n positive integers. Okay, then for this f of n, which is n times n plus 1 divided by 2, I can simplify. This is nothing but n square divided by 2 plus n divided by 2, and which I can easily show is going to be less than equal to n square divided by 2 and plus n square divided by 2 for any n greater than 1, and this is less than equal to n square for n greater than 1. So this I can choose as c times of g of n for n greater than 1, where my g of n is equal to n square. Okay, so by taking c equal to 1 and k equal to 1, we get, using definition of a big O, that f of n is big O of g of n. Okay, or in another word, we prove that the sum of first n positive integers is big O of n square. In the second step, we want to show that f of n is big omega of g of n. So we again write our f of n, which is going to be equal to n times n plus 1 divided by 2, which is equal to n square divided by 2 plus n divided by 2, and which we can easily say is greater than equal to n square divided by 2 for any n greater than 1. Okay, so by taking the constant c equal to half and the constant k equal to 1, and using definition of big omega, we get f of n is big omega of g of n, or in other words, we prove that the sum of first n positive integers is big omega of n square. Then finally, on combining first and second, we get that the sum f of n is big theta of g of n. Okay, and that means the sum of first n positive integers is big theta of n square. And we are done with the proof of this example. So there are two important facts you will say about your big theta notation. The first is when f of n is big theta of g of n, it must also be the case that your g of n is big theta of f of n. And this property holds because fn and g of n, when you write f of n is big theta of g of n, that means they both are is going to be of same order. The second property is which you have when you say that f of n is big theta of g of n, is going to hold true if and only if f of n is big of g of n and f of n is big omega of g of n. And we have seen one example based on that. But now you can extend this one and you can say that if f of n is big theta of g of n, if and only if f of n is big omega of g of n and f of n is big O of g of n, and this is going to hold true if and only if f of n is big O of g of n and g of n is also big O of f of n. Okay, So you have this statement, equivalent statement of proving that f of n is big theta of g of n. And this definition is based on big O, and this definition is based on big O. So if you understand the big O notation, and if you can show that f of n is big O of g of n, and g of n is big O of f of n, then on combining the proof of both of them, you can say f of n is big theta of g of n. So this is the second property about your big theta function. And then we have the last result about big theta notation. So let f of x will be a polynomial of degree n, which can be written as a n x to the power n plus a n minus 1 x to the power n minus 1, and all the way up to a1x plus a of 0, where a0, a1, a2, a of n, they are the real constant, with a of n not equal to 0. That means is going to be a polynomial of exactly degree n. And in that case, you can show that f of x is big theta of x to the power n. We can look at one example based on this theorem. So let's suppose we have a f of x, which is 3 of x square plus 2 of x plus 5. Then for this given function f of x, we can claim that f of x is a big theta of x square. Okay, because it's easy to show in this case that f of x is a big O of x square, and you can also show that f of x is a big omega of x square. So whenever you see a polynomial of degree n, then you can easily determine that f of x is going to be big theta of x to the power n. And we conclude our lecture on this last result. In our next lecture, we're going to discuss the algorithms and how to use this concept in analyzing the time complexity of the algorithm. Thank you.